Hello friends, welcome back. Today we'll be learning about binomial theorem. So what exactly is a binomial expression? Right. So a binomial expression is any algebraic expression consisting of only two terms. Right. So there are only two terms. So what are the examples of binomial expressions? Something like x plus 5, x squared minus a squared, x plus 1 by x. Anything of this nature which has only two terms. X, 5, x squared minus a squared, x, 1 by x. Right? This is called a binomial expression. So what a binomial theorem actually is, it is expansion of any such binomial nth power of a binomial expression. Right? Okay. So binomial theorem is expansion of any power or any exponent of a binomial expression. Okay. So let's say I have this as the binomial expression. Now for writing the general one, instead of pi I will take a. Right? So I write this as x plus a. I raise the whole thing to the nth power, which is any general power n. This actually can be written as nc0 x power n, nc1 x power n minus 1 a, nc2 x power n minus 2 a squared, all the way. I can write some general nth term as n minus r a plus r, then again all the way till nc n minus 1 x a power n minus 1 plus ncn a power n. Right? So this is what the binomial theorem states. The binomial theorem states that x plus a raised to the nth power can be written in this form. Okay. Now look at this formula. This formula is very important and you must know this by heart. Now some of the most important parts. Let us first write this general term. Okay. Now if you look closely, the first term has no exponent of a. The second has first exponent 1. Third has exponent 2. So this term which has exponent r must be the r plus 1th term, right? So tr plus 1 is nc. We see that n is always constant. N is the exponent of the binomial expression. So it is ncr, right? So if it is r plus 1, it will be r here. X power n minus r, n minus r, and then a power r. Always note that the sum of the exponents of x and a, right, or the two terms must be equal to n. Okay. This is our r plus 1 term. Now some salient parts here. NCR is known as the binomial coefficient. Also, suppose we know the value of x here. The value of a, right? Let x be that unknown quantity, the x itself. Whereas we know the value of a, say value of a, if say a is equal to 5 or equal to minus root 3, something like that, right? That means we can now evaluate the coefficient of x, right? So that gives the coefficient of x. So coefficient of x is nothing but NCR into a power r. And if instead of x here we have say 2x, so we get 2 power n minus r, right? So whatever the coefficient of x here is, that the whole thing will become, whatever the coefficient of x in this term, that will become the coefficient of this term, right? Now apart from that, a few properties on these things. Now if you remember, in permutations and combinations we actually came across NCR. right? So NCR is nothing but n factorial by n minus r factorial into r factorial, where NC0 is equal to NCn is equal to 1 because 0 factorial is taken to be 1. Moreover, NCR equal to NCn minus r, right? Also note that there are n plus 1 terms in this expression, right? Right from NC0 we have NCn, there are total of n plus 1 terms, in which the power of x will gradually decrease from n to 0 and the power of a will increase from 0 to n. Also note that since I wrote x here in the as the first term, I wrote it this way. Sometimes just to manipulate the expression, we can write this as a plus x power n, which is still the exactly same thing, and instead of nc0 x power n, we will write nc0 a power n, then nc1 a into x power n minus 1, sorry, a power n minus 1 into x, plus nc2 a power n minus 2 into x squared, right? Now as we know that NCR is equal to NCn minus r, we know that actually makes complete sense, and there's nothing very confusing in that. Okay. Now, okay, so the first one is NCR. So a few properties of NCR, or the binomial coefficient. So NCR is equal to NCn minus r. Now we also read about this property in the permutations and combinations class. C0 plus C1 till Cn is equal to, if I do not write anything in the superscript here for these binomial coefficients, it is assumed that it is by default n. So C0 actually means NC0. It's not n plus 1, it's not n minus 1, it's not m, it's only n, right? So C0 is actually NC0. Similarly for all the other binomial coefficients. Okay, so we had read about this one, but let us see how we can actually prove it. The proof is very simple. We write the binomial theorem for x plus 1 power n. So what is this? C0 x power n, C1 x power n minus 1 into 1, right? So that is 1. C2 x power n minus 2, again 1 squared. C3 x power n minus 3, all the way till Cn minus 1 x plus Cn, right? So x power n gradually decreases from n till 0, whereas the other term, which actually is invisible here because it is just 1 and any exponent of 1 is still 1, that actually makes it just Cn in the last term. Now what if I substitute x is equal to 1? So I see that my right hand side actually becomes C0 plus C1 plus C2 till Cn minus 1 plus Cn. Whereas on the right hand side I have 1 plus 1, that is 2 odd n. Right? So this is how we get our well-known result, that C0 till Cn, the summation of this gives us 2 power n. Now similarly, instead of 1 here, I put minus 1. So what do I get now? Suppose I put x equal to minus 1 in the same expression. Now what do I get? I get 0 is equal to, now this will actually be a bit confusing since x is minus 1 power n, right? The sign will be minus 1 power n into C0. Similarly, okay, so instead of that, I'll actually write it in a different manner. So I'll not put this. I'd rather write this as x minus 1 power n. Right? So if I expand x minus 1 power n, what do I get now? I get C0 into x power n. Now I get minus sign here, right? Everything else is actually still the same thing. It's just that wherever I have an odd power of 1, minus 1, I'll have to write instead of plus minus 1, right? So the second term actually is minus 1 power 1, hence the minus 1 sign here. Similarly, the minus sign here, right? All the way. Now, since my n is not known, I cannot write with certainty for the second last terms, okay? So I'll just keep it that way. Now what I do is, I put x is equal to 1, right? So that gives me C0 minus C1 plus C2 minus C3 all the way till the end. Whereas on the left hand side I have 1 minus 1, that is 0, right? Now this is a very interesting thing. You see that all the even are, right? They have the plus sign, whereas all the odd have the negative signs, right? So you can actually write this as, and this goes on till the end uniformly, right? So you can write C0 plus C2 plus C4 is equal to actually C1 plus C3 plus C5. And any guesses what they both are actually equal to? Well, you see that, but if you just add this equation and this equation, you will see that the odd r's, that is C1, C3, all of them will cancel, and C0, C2, all of them will add up. So that will give us that C0, C and all these are equal to actually 2 power n by 2, right? Since there are all of them have twice those terms. Now since C1, C3, C5 are equal to them, they are also equal to this value, right? So this property states that okay. 2 power n minus 1. So all these binomial coefficients alternately, when they are grouped, they all have the same value, right? The summation of both of these groups will have the same value, which is equal to 2 power n minus 1. Okay. Now one more property. This one is very handy in solving questions. So I'll just write it first. Okay. So NCR by R plus 1 is equal to N plus 1 C R plus 1 by N plus 1. Okay. So this actually is pretty simple to arrive at. What you do is, I'll first write the LHS. LHS is NCR, that is N factorial by N minus R factorial into R plus 1. Right? Now I see that R factorial into R plus 1 is nothing but R plus 1 factorial, right? So I have N factorial by N minus R factorial, R plus 1 factorial, right? But now, this part, the second exponent, I can write that as N factorial by N plus 1 minus of R plus 1. Right, I just manipulate it, I write it this way, so as to accommodate this next part. So I write this as N plus 1 minus of R plus 1, that still is N minus R, right, into R plus 1 factorial. Now since I have written N plus 1 here, I multiply the numerator and divide the whole thing by N plus 1, right. Now N factorial into N plus 1 is nothing but N plus 1 factorial. So I have N plus 1 factorial by N plus 1 minus of R plus 1 factorial, the whole factorial, into R plus 1 factorial into N plus 1. That is nothing but N plus 1 C R plus 1 by N plus 1, right? So we actually see that there are there are some important things to note here. First of all, whatever r you have here, the denominator should be just one more than that. Not one less, not equal to, not two more. It should be exactly one more than that. Otherwise, this proof doesn't work and you will not get the result. Right? Moreover, the next part is instead of n here, it will become n plus 1, which will be both the n plus 1 here as well as that in the denominator. Okay. So now we look at once this property is also proven, we now look at the middle term of the expansion. Now, as I had explained earlier, the binomial coefficients, they actually increase first, reach a maximum, and then again decrease, right? Because we see that NC0 and NCN both have the value 1, whereas it cannot take positive integral values, so it always increases. And the middle term actually is numerically the greatest number, right? Now that is why the middle term is sometimes very important, and there are actually two cases. The first is when n is even. So when n is even, the middle term is the n by 2 plus 1th term. And when n is odd, it is n minus 1 by 2, there are two terms, right? And n plus 1 by 2. Now why this happens is obvious, because when there are n terms, when the exponent is n, there are n plus 1 terms, right? So when n is odd now, so n plus 1 and n minus 1, both of them will be still even, whereas n by 2 plus 1 can now be actually an integer, and hence for even this should be n by 2 plus 1. For odd, there are two possible terms, both of them have the same binomial coefficient, and both of them are the largest numbers. Okay. Now, though the binomial coefficients are the largest at the middle term, but in the expansion of a binomial expression, you may not always get that as the numerically greatest term, right? So how exactly do you find out the numerically greatest term? So how exactly do you find out the numerically greatest term in a binomial expression? Now, the procedure is very simple. What we do is, we find out the tr plus 1 by tr, right? And moreover, since all binomial expressions will not be guaranteeing us a positive coefficient, so we take the modulus of this, right? Because all we are interested in is the numerically greatest term. We are not bothered. We don't bother ourselves with the sign of the term. Okay? So minus 200. If there is a term, so minus 200 x power 4, and there is 100 x power 3. So we still consider minus 200 x power 4 to be having the numerically greater term, and hence the minus sign is not important. Okay? So we take the mod, and now that should be greater than 1, right? So if we can analyze the general r plus 1 term and the rth term, because we always see that there is a relation between all these consecutive terms, right? So they either increase first and then decrease, or they decrease first and then increase, right? So we see that this must be the case, and analyzing this will always give us our numerically greatest term. We will take up a few questions on this, and it will be very obvious. This concept will be clear from that. Now, while proving a few properties in the previous slides, we did something which I will be taking now. So, if I write x plus a for n, in my usual way, C0 x bar n, C1 x bar n minus 1a, C2 x bar n minus 2 a squared, and all the way. I'll intentionally not write the later parts. We'll see why that. So, now, if I write x minus a power n, right? So instead of a now I have minus a. So that is now, wherever there is odd exponent of a, I would have a negative sign. Right? Okay, so this one actually should be negative, because we know that the next one is nothing but a cube. Now a cube is again, it should have negative, minus a cube actually. Right? So when I add these two up, what do I get? The left hand side is simple, x plus a power n plus x minus a power n. Whereas on the right hand side we see that all the odd exponents will get cancelled. So what I have is nothing but, and the even parts actually add up. Right? So I have 2 times c0 x power n plus c2 x power n minus 2 a squared, c4 x power n minus 4 a power 4, all the way till the last even exponent of a. Okay, so this is again a very important property of the binomial expansion, right? So if I have x plus a power n and I have x minus a power n, when I add them up, all those so here I have a and minus a, right? So that is why the odd powers will get cancelled out. Had this been a plus x power n plus a minus x power n, all the odd powers of x would have cancelled out. Right, so that is the part you have to be careful about. Similarly, instead of adding, if I subtract the second from the first, so you see that instead of now if I subtract this, if I put a minus sign here, I'll have a minus here and here a plus, similarly minus, plus, and subtracting now is nothing but addition of these two now, right? So I see that these things will cancel now, right? Not these ones. all the even exponents of a will cancel now. So now actually a power 0 will also be considered as an even exponent, and that is how the first term is also accounted for. Now this is equal to 2 times c1 x power n minus 1a plus c3 x power n minus 3 a squared, a cube, all the way in the end. So these are two very important properties. Will be used in a lot of examples or questions to say solve or prove a few results. Okay. So x plus a power n plus x minus a power n gives you 2 times c0 x power n plus c2 x power n minus 2 a squared. So all these even exponents of a. Similarly, x plus a power n minus x minus a power n will give you all the odd exponents of a. Let us now take up multinomial theorem. So multinomial theorem is nothing but the generalization of binomial theorem. We will be taking up only a small part of this. So anyway, say I have instead of say x plus a, which I could have written as x1 plus x2, right? Binomial. Now I have multinomial, so I have x1 plus x2 plus x3, we'll say xm. Okay. So suppose I have x1 plus x2 x3 till xm. So since there are m here, which is just a general m, which is more than 2, right? So I'll be using the multinomial theorem here. Now what this is actually used for in our cases is in the following kind of examples. So suppose all of these are actually integers. Right? Suppose all x1, x2, x3 and xn are integers, and suppose their sum is a constant n. Okay. So what are my assumptions here? First, that all of these are integers, all these different expressions, different terms, x1, x2, x3, and also that their integers, their sum is a fixed thing, a fixed constant n. Okay. Now let there be a specific range for all these values. Okay. So let x1 take values only from a1 to b1. We can assume them to be integers. Otherwise, the equality sign will have to be removed. Similarly, the range for x2 is say a2 till b2, right? All the way till range for xm as am and bm. So the total number of non-negative integral solutions that is equal to n plus m minus 1 c times m minus 1. Okay. So in this kind of question, these kind of questions actually come in permutations and combinations, which have their basis in binomial theorem, right? So it's nothing but a generalization of binomial theorem, and we see that we'll take a few questions to clarify this thing. So these are the important results. The first is the non-negative integral solutions of this equation. The non-negative integral solutions of this equation is n plus m minus 1 c m minus 1. These many solutions exist. And if you know non-negative, right? So that means 0 is also actually included. But if you take strictly positive, okay, so 0 is also not included. Only positive integral solutions. That is equal to n minus 1 c m minus 1. Okay. So these are the two most important properties we are concerned with. We will take up a few questions to clarify this. Okay. Now let us also look at say any given number n. Right. I assume the difference between composite number and prime number is well known. So let us for generalization, let us just assume that n is a composite number, because in case of prime number this will become too trivial. Okay. So let us write the prime factorization of n. Okay, so let the prime factorization of n be p1 power alpha 1 into p2 power alpha 2 into p3 power alpha 3. Okay, where p1, p2, p3 are all prime numbers, and alpha 1, alpha 2, alpha 3 are obviously their exponents. Okay, so some of the properties we are actually concerned with are, first, how many total divisors exist for n, right? So the total number of divisors are any numbers which will divide n, right? So the total number of divisors is equal to alpha 1 plus 1 into alpha 2 plus 1 into alpha 3 plus 1 till the last one. Say the last one is pn power alpha n, so alpha n plus 1. Okay, instead of n I'll rather take this as m. You may get confused with the number n itself, right? So it's alpha 1 plus 1 into alpha 2 plus 1 into alpha 3 plus 1 till alpha m plus 1. Okay. So suppose we have a number of 25. I know this is a number 5 squared, and I know all its roots, right? All its divisors 1, 2, 5 and 25. Okay. So actually 1 is never considered as a root here. Now if I find the total number of divisors here, so this is my p1, this is my alpha 1. Total number of divisors is nothing but 2 plus 1, that is 3. Right? 1 is not considered as a divisor usually, and that's how you arrive at this formula. Now again, what is the sum of all these divisors? We have a beautiful formula for this. Now that is equal to p1 power alpha 1 plus 1 minus 1 by p1 minus 1 into P2 power alpha 2 plus 1 minus 1 by P2 minus 1. Similarly, P3 power alpha 3 plus 1 minus 1 by P3 minus 1. Get the drift, right? So this will be actually all the way till the last prime number, and that raised to its exponent plus 1 minus 1 by the prime number minus 1. Okay, so in case of 25, we will have 5 cube minus 1 by 5 minus 1. Okay, and now the last thing concerned about this, well, we write all this if we know the exponents of these prime numbers, right? But what if we don't know the exponents of these prime numbers? How do we write them? Well, that is actually given by a very simple formula. The exponent alpha 1 will be given by n by p1 plus n by p1 squared plus n by p1 cube till you finally get no more value. Okay, now these square brackets are not any normal square brackets, they are actually greatest integer function. Okay, so these are actually greatest integer function. Well, what that means is, say greatest integer of 1.5 is actually 2. Instead of arrow, I should actually write this equal to, because that's what makes sense. Sorry, it's not 2, it's 1. Right? So greatest integer function means the greatest integer not exceeding that number. So greatest integer of 1 is 1, whereas greatest integer of 0.5 again is 0. Similarly, greatest integer of minus 1.5 is not minus 1, it's minus 2. So that's it for the theory and results of related to binomial theorem. In the next video we will be discussing a few questions covering almost all the types of questions in binomial theorem. Thank you.